Okay, so now let's continue from where we stop. This is the NECO physics. NECO physics. So we are under the theory aspects. So I've answered number 1 to 4, which I termed or I called part 1. So let's take this part as part 2. I stopped at number 5A. I've stopped 1 to 4. So I was about, let's start from 5A. 5A says, what is vaporization? NECO physics, that's National International Council. So what is vaporization? Vaporization is the state at which a liquid substance changes into a gaseous state or changes into vapor without change in temperature. That is the definition of what? Vaporization. Okay, so your methylated spirit can vaporize, your petrol can vaporize. Okay, so now 5B. 5B says, state one effect of increase in heat for a temperature range of 50 degrees Celsius to 100 degrees Celsius. State one effect of increase in heat for a temperature range of 50 degrees Celsius to 100 degrees Celsius on plastic, and 2 on iron. That is, when you increase the temperature of plastic from 50 to 100, what happens? When you increase the temperature of iron from 50 to 100 degrees Celsius, what happens? So let's take plastic first. You know, plastic is an amorphous substance. Are you there? Plastic is an amorphous substance. So it doesn't have a definite melting point. So once we increase the temperature of plastic, any plastic, from 50 degrees Celsius to 100 degrees Celsius, it begins to degrade. It begins to break. It begins to ship. Are you there? So it begins to degrade gradually. So it softens gradually, and that's the phrase they are looking at. They are looking for. Once you increase the temperature of plastic from 50 degrees Celsius to 100 degrees Celsius, so it softens gradually. It softens gradually. Okay. Now, on iron, once you increase the temperature of iron from 50 degrees Celsius to 100 degrees Celsius, the molecules of the iron, they will become energized. Are you there? That is, their average kinetic energy will increase. So that is the effect on iron. So the molecules of iron will become energized. Are you there? And those energetic molecules, they will move faster. So meaning that their kinetic energy will increase. Iron will not melt. It will not melt because 100 degrees Celsius is not the melting point of iron. No, 100 degrees Celsius is not the melting point of iron. Okay, so that is the effect of increase in temperature of plastic and iron from 50 degrees Celsius to 100 degrees Celsius. Now let's go to number 5. Let's go to number 6. Number 6A says, how are stationary waves formed? How are stationary waves formed? You know, a stationary wave is formed when two waves of the same amplitude and frequency, traveling in opposite directions traveling in opposite directions, superimposed, or you say overlapped. When two waves of the same amplitude and frequency traveling in opposite directions overlap, so a stationary wave is formed. So another word for stationary wave is standing wave. Are you there? Naturally, the two waves are incident wave and reflected wave. Incident wave, in most cases, it is incident wave and what? Reflected wave. For example, we have a closed pipe. When you have a closed pipe and you talk, sound waves will come out from your mouth. It will pass through the closed pipe. Let us be having a pipe this way. This is a closed pipe. So once you carry, let us assume your mouth is here. Once you speak, sound waves comes out from your mouth and incidents on this closed end. Okay? Then once it's incident on this closed end, it is reflected. It is reflected back. Are you there? So when this incident ray and reflected ray combine, are you there? A standing wave. Can't you see that it is the same wave? Both of them, incident wave, reflected wave, both of them have the same amplitude and frequency. Are you there? So when they combine together, let me show it in this form. So when we have one wave traveling in this direction, are you there? That is the direction of traveling of one wave. Then the second wave traveling in opposite direction. Maybe it's traveling in this particular form. Let me have a green marker for that. Can you see this one is traveling in this direction? In this direction. While the other one, the red ink, is traveling in this direction. It's traveling to the right. Traveling to the right. But the green wave is traveling to the left. So this is what we call standing wave. But I have to say how are stationary waves formed? Are you there? You just tell them stationary waves are formed when two waves of the same amplitude and frequency overlapped or superimposed. So if you want to go further, these two waves they can overlap constructively and they can as well overlap destructively. When the two waves are in step or when they are in phase, they will overlap constructively. Are you there? They will overlap constructively. It means that their resultant amplitude will be high. But if they are out of phase, that is out of steps, they will overlap destructively. Okay? That is, the resultant amplitude will be zero or minimal. Just like when you have a string, and the two ends of a string is fixed at both ends. You fix them at two ends. You fix them. Then you now draw the spring at any part. You draw it and you leave it. It vibrates. Are you there? At a particular time, it dies down. The vibration dies down. So that is a standing wave. That means one wave is incident wave, the other one is reflected wave. Two of them combine together to form a standing wave, and their combination is destructive. That is why the vibration of the spring will come to a stop. All right, let's now see that 6A. Let's go to 6B. 6B. For 6B, we are given a sketch of a diagram. They gave us this for 6B. For 6b, we're having a kind of a sketch graph. Okay, something like this, like this, like this. 1, 2, 1, 2, like this, okay, like this. Another one. Okay, this is what we are given. Okay, they call this one, they said this side is y in meters, that the vertical axis y in meters, the horizontal axis are x in meters, x in meters. So they now said from this point to this point we're given distance from the beginning to the end. They put arrow here. Beginning to the end is 4 meters. 4 meters. Okay. They now said that this column 6b. Now says calculate the wavelength of the waveform. This is the waveform, right? Calculate the wavelength of the waveform shown in the diagram below. You calculate the wavelength of the waveform shown in the diagram below, or this. Now, what do? You know, when you go back to terminologies in wave, they are called wavelengths. Wavelength is the distance between successive crests or successive trough. The distance between successive crest or successive trough. This is a crest. The mountains are the crests. Either while the bow, while these bows are we call troughs. So this is a crest, this is a crest, this is a crest, this is a trough, this is a trough. Are we together? So distance between successive crests or successive trough. So you can look at this. This crest to this crest give you one wavelength. One wavelength. This trough to this trough will give you another wavelength, making 2 wavelengths. Then the remaining half in this one will give you half wavelengths. That is, everything becomes 2.5 wavelengths. That's how to count it. Crest and crest, that's one wavelength. Trough and trough, that's another wavelength, making 2 wavelengths. Then the remaining one here, that's half, that's 2.5 wavelengths. So that means the waveform runs from this side to this end. Are you there? That means the length, that means total length equals to 2.5 wavelengths. That means L equals to 2.5 wavelengths. Okay, so what's our L? Let's look at our L is 4 meters already. That is 4 equals to 2.5 is 5 over 2 wavelengths. Okay, or 2.5. So we have 4 equals to 2.5 wavelengths. Making wavelength is stop there. So wavelength equals to 4 over 2.5. Are you together? So 4 divided by 2.5, that gives us 1.6. So that means the wavelength is 1.6 meters. 1.6 meters. That's 4 divided by 2.5. 1.6 meters. So that is the wavelength that we are asked to find. So the question says calculate the wavelength of the waveform shown in diagram below. That's 6b. So let's go to 7a. 7a is not a calculation question. 7a says, why does sound not travel through vacuum? Chinikini. Why does sound not travel through vacuum? You and I know that sound wave is a mechanical wave. Under 2 types of waves. We have mechanical wave and electromagnetic wave. So a mechanical wave is a wave that requires a medium for its propagation, that is for its production, that is for its transmission. Okay, a mechanical wave requires a medium for its propagation. So sound wave is an example of a mechanical wave. Are you there? So why does sound, now look at I've not answered a question, I'm just trying to prepare your mind. Now, why electromagnetic wave? Those ones do not require a material medium or a material media, plural, for their propagation. I just mentioned between mechanical and electromagnetic wave. Now, why does sound not travel through vacuum? Before sound can be propagated, before sound can be transmitted, the medium through which it is to be transmitted must have molecules or particles. The medium through which sound is to be propagated must have molecules or particles. When we're talking about medium, we're talking about water, talking about air, talking about string. Do you understand? So if sound cannot travel through vacuum, because in vacuum there's no air. Are you there? But sound will travel through a medium where there is air, because air contains molecules. Are you there? Or particles. So sound does not travel through vacuum because vacuum has no air. Vacuum has no what? Air. In vacuum has no air. So air is needed in that vacuum. The vacuum has no air. So the sound itself, the sound itself is transmitted or propagated through the vibration of the particles or molecules of the medium. Sound is transmitted or travel through the vibration or propagation of the medium. Now that vacuum has no air, so there won't be vibration or vibration of the particles of the medium. That's the reason. 7A. Okay, that's 7A high. Now 7A high. Oh, 7A has been answered. So now round figure 1, 7A I now. When is critical angle said to be subtended by an incident ray of light? When is critical angle said to be subtended by an incident ray of light? Incident ray. When is critical angle said to be subtended by an incident ray of light? The critical angle will be subtended when the reflected ray of the incident ray, when the refracted ray of the incident ray lies at the interface of the two media. So that is critical angle. Are you there? That's what critical angle. So when the critical angle will be subtended when the refracted ray of the incident ray lies at the interface of the two media. Now, the answer says state one of the conditions for total internal reflection of an incident ray to occur. State one of the conditions. Now, one of the conditions is that light must travel from an optically dense medium to an optically less dense medium. Light must travel from an optically dense medium to an optically less dense medium. That is, if you have air, you have water, and you have glass. Are we together? So glass is denser than water. So when light travels from glass to water, are you there? Critical angle, total internal reflection is bound to occur. Or when light travels from water to air, because water is denser than air, total internal reflection is bound to occur. Are we together? But when light travels from air to water, total internal reflection does not occur because air is lighter than water. Likewise, when light travels from water to glass, total internal reflection will not occur because water is lighter than glass. But when it goes from glass to water, it will occur. When it goes from water to air, it will also occur. So light must travel from an optically dense medium to an optically less dense. You must put the word optics, optically. You must put that word. Are you there? So that is one of the conditions. Are you there? Another condition is that the angle of incidence in a denser medium must be greater than the critical angle. The angle of incidence in a denser medium must be greater than the critical angle. That's another condition. Though we have to state one as state two. So let's go to number 8. Number 8A. Number 8A says, what is lost volts? What is what? Lost volts. What is lost volts? Lost volts. That's number 8A. What do you think a lost volt is? Let me clean this side. Lost volts. Let me show you something. Okay, let me define this. Lost volts is the potential difference. It is the potential difference obtained. Are you there? When a cell is the potential difference obtained as a result of the difference as a result of the difference in the EMF of a cell when it is in a closed circuit and when it's in an open circuit and when it is in a closed circuit. I repeat, lost volts is the voltage obtained. Lost volts is the voltage obtained as a result of the difference in the EMF of a cell when it is in an open circuit and in a closed circuit. That's one way of defining it. Another way of defining lost volts is to say, another way of defining to say that it is the voltage obtained as a result of the product of the current flowing through a circuit and the internal resistance of the cell. That's another way of defining it. Look at it. If you have I equals to EMF over R plus R, as a big R plus small r. Okay, so if you like cross multiply, you have capital E equals to I times big R plus I times small r when you cross multiply. Okay, this I times small r is the lost volts. Are we together? So can I make IR the subject, as in I times small r is subject? Now I have capital E minus capital I multiplied by big R equals to capital I small r, as you can see. So this I small letter r is lost volt. Are you there? It can be lost volt is the voltage obtained as a result of the product between the current flowing through a cell and its internal resistance. Or you say this is EMF when the cell is not connected to anything. Okay, Why this I multiplied by big letter R, it is when it is bringing difference when the cell is connected to a circuit that is connected to a resistor, an external resistor. Are we together? So that is the definition of lost voltage. Any one of the two goes. For example, now when you look at a Leclanche cell, the number, the EMF of a Leclanche cell is 1.5 volt approx. Okay, so this cell, normally we have not used it in any circuit, it is 1.5 volts. But when you use it to perform experiments in the lab, you connect it to form a circuit to an external resistor, and you connect a voltmeter in parallel to it. If you measure if you read out what you have on the voltmeter for the Leclanche cell, you found that it will not give you 1.5 volts. It might give you 1.48 volts when in use. Okay, that is in a closed circuit. The difference between 1.5 and 1.48, are you there? 1.5 minus 1.48 will give you is 0.02 volts. So this is the lost volts as a result of the internal resistance of the cell. All right, 8b says state two advantages of secondary cell over primary cell. So state two advantages of secondary cell over primary cell. A secondary cell can be recharged when it runs down, but a primary cell cannot be recharged when it runs down. Are you there? So a secondary cell can be recharged when it runs down, but a primary cell cannot be recharged when it runs down. Another advantage of a secondary cell is that a secondary cell has a low internal resistance, hence it gives a large current, hence it produces a large current. But the primary cell has high internal resistance, hence it produces a low current. Okay, that is for number 8b. That's the two advantages of a secondary cell over a primary cell. When I'm talking about a secondary cell, we are talking about accumulators. We are talking about the lead acid accumulator, which is the car battery. That's one example. Are you there? That's one example. That's an example of a secondary cell or accumulator. Are you there? The car battery. Then the primary cell, like Leclanche cell, is the primary cell. Okay, the Tiger or Lion battery that we use, okay, that is a primary cell. That's 8b. So let's now go to number 9a. 9a says state the condition under which resonance occurs in an AC circuit. States the condition under which resonance occurs in an AC circuit. AC circuit means alternating current circuit. A circuit in which alternating current is flowing. So what are the conditions? Are you there? Or what is the condition? You can state any one of these. You can say resonance occurs when resistance is equal to impedance. Oh my goodness. When resistance is equal to what? Impedance. Capital letter R represents resistance in AC circuit, and then the Z represents impedance. So when resistance is equal to what? Impedance, resonance occurs. Or you can as well say, when the inductive reactance is equal to the capacitive reactance. Oh my goodness. That is when X subscript L, which is the inductive reactance, is equal to X sub C, which is a capacitive reactance. You can also say like that. Are you there? So when resistance is equal to impedance, or you say when inductive reactance is equal to capacitive reactance. Okay. And you can also say that when current, another condition, that when current in the AC circuit is maximum. Yes. When current in the AC circuit is maximum, resonance occurs. That's another way, that's another one to say. You see, when current in the AC circuit is what? Is maximum. Look at the graph. When you sketch a graph of current I against frequency, the current flowing through the circuit, which is alternating current, and the frequency, you know, it is a waveform, and the frequency, when you plot it, you get something like this. It goes up, then it comes like this. So this particular point, when you trace it to the vertical axis, this is the maximum current, mass, high mass, maximum current. Then this particular one, when you trace it to the x-axis, that is F naught, F subscript 0, that is a resonance frequency. So resonance frequency occurs when the current in the circuit is what? Maximum. So I've given you when current is maximum, I subscript M mass. So I've given you 3 conditions. Are you there? So you give the examiner one. Okay, let's see. That's number 9A. Let's see 9B. 9B is a calculation question. Don't forget, I've shown you if you ask to sketch the graph of current against alternating current in a circuit against frequency. This is what you have. Okay. Oh, let's have 9B. 9B is a calculation under alternating current circuit. A series consists of 5 ohms. So a series circuit of 5 ohms resistor. A series circuit of 5 ohm resistor, 2.3 millihenry inductor, 2.3 millihenry inductor, and 0.03 microfarad capacitor is connected to an AC source. Calculate the resonant frequency. We are given pi as 3.14. I repeat the question. A series circuit of 5 ohms. Let's list out the parameters. A series circuit of 5 ohms resistor. That means we are given capital letter R equals to 5 ohms. That's a symbol of 5 ohms. Capital letter R equals to 5 ohms. Okay. Then 2.3 millihenry inductor. That means capital letter L has been given. Capital letter L has been given. So capital letter L equals to 2.3 small m, that's milli, capital H, that's Henry, that's units. Okay, 2.3 millihenry. Then and is 0.03 microfarad capacitor. Then the capital C has been given. We represent capacitor by capital C. Capital C equals to 0.03 micro is mole, then farad. 0.03 microfarad. Okay. There's a need. They said calculate the resonant frequency. You are looking for F subscript 0. That's F subscript 0. That is what we're looking for. Question mark. That's resonant frequency. Are we together? So the need for you to convert the 2.3 millihenries to Henry. You convert it 2.3 millihenry to Henry. How do you do that? You divide by 1000. Okay, milli means thousands, a thousand. So that gives us equals to 2.3 times 10 raised power minus 3 Henry. Or you say 2.3 over 1000. It will give you that. Give that 2.3 times 10 minus 3. Okay? So the inductance of the inductor has been converted, which is error. Now C, capacitance of the capacitor needs to be converted from microfarad to farad. This micro, which is mu, that thing that look like U. So how do you convert from microfarad to farad? How do you remove that mu? That thing that looks like U, well, which is not U, either call it mu, is for you to divide by 1 million or multiply it by 10 raised to the minus 6. Okay, so we now have it as equals to 0.03 times 10 raised to the minus 6 farad. It has been converted. Alright, you can be jotting down. So as I'm speaking it out, you can also be writing it down. So that is 0.03 times 10 to the minus 6 farad. That is our C, capacitance of the capacitor. Can we now bring out our suitable formula for resonant frequency? Formula for resonant frequency is F naught equals to 1 over 2 pi square root the product of L and C. Resonant frequency formula F naught equals to 1 over 2 pi multiplied by the square root of LC, capital L, capital C. Can we have it again? F naught equals to 1 over 2 pi square root LC. L and C are inside the square root. Okay, let's now substitute. It says calculate the resonance frequency. So let's substitute. So equals to 1 over 2 times pi is 3.14 multiplied by square root of L and C. What is square root of L? What is square root of L? What is L itself? L is 2.3 times 10 raised to the minus 3 multiplied by C is 0.03 times 10 raised to the minus 6. Okay. Alright, we are there. At the square root of 2.3 multiplied by 10 raised to the minus 3 times 0.03 times 10 raised to the minus 6. So you can use the calculator for the whole of this. Are you there? At once. But to me, let me see, F naught equals to 1 divided by 1 divided by 1 divided by. So 2 times 3.14. That's 2 times 3.14 is giving me 6.28. That's 6.28 multiplied by the square root of this one is F naught, F subscript naught resonance frequency. So now I'm just breaking it down. Your calculator can do everything at once. I want to break it down. 2.3 times 0.03 inside the square root. 2.3 times 0.03, that gives us 0.069. 0.069. 0.069 multiplied by, now 10 raised to the minus 3 times 10 raised to the minus 6, that gives us 10 raised to the minus 9. Okay, minus 3 minus 6, that's minus 9 under indices. This one is 6.28. Are we there? Okay, don't forget, I'm just trying to break it down using mathematical steps. Okay, so let's now have F naught equals to 1 over 6.28 times square root of, so this is 0.069 times 10 to the minus 9. I want to make that 10 to the minus 9 an even number so that I can easily find its square root. Okay, 10 so I can easily find the square root. Okay, that means it's either, let me just make it, this is 0.069, let's turn it to we'll bring the points here, 1 2, or this is 69 times 10 raised to power minus 3, non-standard form is 0.069 to non-standard form, or to standard form rather, to standard form, that's 69 times 10 raised to power minus 3. 69 times 10 raised to power minus 3. Just I want to take it from decimal point. I want to take it away from decimal point. So this is 9. Look at it. 1 2 3. That's 9 times 10 minus 3 multiplied by 10 raised to power minus 9. Okay. As you can see, minus 3 minus 9 give me minus 12. That's what I want. I want an even number, so I can easily find the square root. So we now have f naught equals to 1 over 6.28 multiplied by square root 69 times 10 raised to power minus 3 times 10 raised to power minus 9. That gives us 10 raised to power minus 12. Okay. So I have square root 69 times 10 raised to power minus 12. That is 6.28 times. So 1 over the whole of this. Alright. Aha. So now I can now conveniently find the square root of 69 and find the square root of 10 to the minus 12. So that gives us f naught equals to 1 over 6.28 times square root of 69. Square root of 69 is giving me 8.3 to one decimal place. 8.3 square root of 69, that's 8.3. 8.3 multiplied by square root of 10 to the minus 12 will give me 10 to the minus 6 times 10 raised to the power minus 6. You know, square root of 10 to the minus 12, the square root will come up as half, and the half will multiply the 12 at the top. So 12 times half will give you 6, so the minus 6. So let me write, having 1 over 6.28 times 8.3 times 10 raised to the power minus 6. Put together. So the 10 to the minus 6 will go up. Let me come here. F naught equals to the 10 to the minus 6 will go up, becomes 10 raised to the power 6, all divided by that 10 raised to the power 6 at the top now, all divided by that 10 to the minus 6 at the denominator will come up and becomes 10 raised to the power 6. Then we now have 6.28 times 8.3 as denominator. 6.28 multiplied by 8.3, and that gives us 52.124. 52.124. So finally 10 raised to the power 6 divided by 52.124. You know 10 raised to the power 6 is 1 million. That's 1 2 3 4 5 6 zeros divided by 52.124. Okay, that gives us 19,185 to the nearest whole number. 19,185. Final answer. So F naught equals to 19,185 has that's unit 19,1, that is 19185 as the whole number. So let me do again 1 million divided by 52.124, that's 19185 to the whole number approx has. So this is the resonance frequency. You can convert it to standard form if you like. So and that will be 1 2 3 4 1.9 2 approx times 10 raised to power 4 hours, if you like. So that's answer to B, 9B. So we are going to number 11. So this is, we do number 10 and number 11. Number 10A. Number 10A says, mention 2 types of unit cells. Mention 2 types of unit cells of a cubic crystal other than face-centered cubic. Mention 2 types of unit cells of a cubic crystal other than face-centered cubic. You know, we have types of unit cells. Types of unit cells. We have the face-centered cubic, known as FCC. Body-centered cubic, BCC. We have hexagonal close packing, HCP. You know, some people also put simple cubic crystal, simple cell. Okay, you can also put that. So, but we have face-centered cubic, FCC, body-centered cubic, BCC, then hexagonal close packing, HCP. So we mention, they say we should not mention face-centered cubic, we should mention another 2 apart from that. Give them body-centered cubic, BCC, and hexagonal closed packing, HCP. Okay, and sometimes we also write simple unit cells. Simple unit cells, you can give them also. It will be marked for you. That's number 10A. Now 10B is a simple calculation. They said calculate the half-life of a radioactive element. Calculate the half-life of a radioactive element of decay constant is 0.0385 per second. Calculate the half-life of a radioactive element of decay constant 0.0385 per second. That one is very, very simple. Let's quickly solve that. I think that's the last calculation for this particular part. So we are given the decay constant as 0.0385. So we use lambda to represent decay constant. Lambda, that's 0.0385 per second. So that we are given is 0.0385 per second. We have to calculate the half-life. Half-life is capital letter T subscript half. We use capital letter T subscript half equals to question mark. That's to represent half-life. Don't forget, I'm writing the 0.0385 per second. That's lambda, and lambda here represents decay constants. Can we now have our suitable formula to solve that right now? Formula for half-life. Okay, formula for half-life. So half-life formula T, capital T subscript half equals to 0.693 over lambda over decay constant. Capital T subscript half, that's half-life, equals to 0.693 divided by decay constant. Decay constant is lambda, as you can see on the board. 0.693. So can we now substitute? We are only substituting the denominator. The numerator is already a constant, 0.693. 0.693 divided by what's our lambda? 0.0385. Okay, that's 0.0385 divided, so 0.693 divided by 0.0385. Can you now bring your calculator, you punch your calculator and see what you're going to get there? And that's 0.693 divided by 0.0385, and that was given us 18 on dot, just a whole number 18. So that's giving us 18. Mr. Man, if you don't put your unit, you are wrong. That's 18 seconds. Boy, if you don't put your unit, you are wrong. That's 0. If you don't put your unit, that's 18 seconds on dot. That is a whole number. All right. That's the answer to number 10B, which says calculate the half-life of a radioactive element of decay constant 0.0385 per second. So the half-life is 18 seconds. That means every 18 seconds the radioactive substance decays. Now the last question is number 11. We are having 11A and 11B. Okay, 11A and 11B. 11B says draw a label diagram of a photocell. A photocell will convert light energy into electric energy. It receives the light energy from the sun. Are you there? So if you want to explain it very well, when the light energy itself is carrying photon, according to Compton effects, the light energy is carrying a particular particle called photons. Now, when the photons interact with the metal cathode, the cathode is a metal itself. The light shines or strikes the metal cathode. Are you there? So the cathode, metal cathode, has its own particles, which we call molecules. Then it is carrying electrons. The mobile particles in metal are what? Electrons. So the electrons interact with the photon. The electrons in the metal cathode interact with the photons from the light, from the sunlight. Are you there? So the photon, which is a light particle, which is carrying a certain amount of energy. Are you there? So will be imparted on the electron. That is, the energy will be absorbed by the electron. The electron will now be free from the attraction of the positively charged nucleus. Are you there? That they will knock out. I've been missing, chemistry is there, physics is there also. So in that particular explanation, so they say we should just draw a label diagram. I'm just trying to ginger you with the explanation behind it. All right, let's see how we can draw the diagram. A photocell converts is a cell that produces a current by converting solar energy towards electric energy. All right. Let's assume we are having the metal cathode like this as a curve. Part of it, this is metal cathode. Okay, and let's assume we are having sun somewhere. This is sun, the sun that will give us the light that we need. That's the sun. So light rays comes from the sun, it shines on it illuminates this plate, which is a metal plate. Are you there? Okay, it strikes it. Okay, and then when it incidents, it is what? Reflected. Are you there? It's reflected. And that reflection is not ordinary reflection. That reflection is the emission of electrons in the metal. Emission of electrons in the metal in this way. So the electrons emitted, they migrate to the anode. You can have anode as a plate like this, a vertical plate as the anode. Are we together? So the anode is a positive electrode, while this cathode here is a negative electrode, minus. You must show all those things. That's what they are looking for. So now the metal that is illuminated by the sun's rays of light is negatively charged. Is negatively charged. That's minus. Call it cathode. While this other end is the positive electrode called anode. So anode, the anode on the other side is cathode. Is cathode. Small time will be done. So this is cathode, this is anode. Are you there? So you connect the two, you connect them to a cell to make a battery, just to complete the circuit. Okay, to complete the circuit. It's coming here to complete the circuit. Are you there? So this cathode and anode, they are situated in a glass tube. They are situated in a glass tube, evacuated glass tube. Okay, evacuated glass tube. You can take it this way. Evacuated glass tube. Okay, evacuated glass tube. As you can see, so the anode and cathode, they are inside the evacuated glass tube. Okay, so the electrons emitted from the cathode migrate to the anode. Why? Please don't forget that this one is short dash and a long dash. Then short dash and a long, that is negative terminal. You don't forget that, please. Negative terminal. Short dash and a long dash. Okay, short dash and a long dash. That is negative terminal of the battery to the positive terminal of the battery. So the negative terminal side is connected. The negative terminal of the battery or cell is connected to the cathode side. Why? Because the negative terminal is negative, the cathode is also negative, so that there will be repulsion of electrons. So that electrons will be repelled from it. So the electrons repelled from the cathode will migrate to the anode. Anode is positively charged. Are you there? Anode is positively charged. So the cathodes, the electrons are negatively charged. They will migrate to the what? They are attracted by the anode, which is positively charged. Don't forget that the negative terminal of the cell or battery will be connected to the cathode, while the positive terminal, which is the long one, is connected to the anode. Do not forget, and that's what the examiners are looking out for. Okay, short and long. Okay, that is the drawable diagram of a photocell. The last question: mention two applications of a photocell. Mention two applications of a photocell. Two applications of a photocell. Okay, number one, you can use a photocell in automatic street lights. Automatic street lights use photocell. Are you there? Then automatic doors. Automatic doors use photocell. Burglar alarm. Burglar alarm also use photocell. You see, you can have more. You can have a lot of examples. Okay. Television cameras use photocells. Some television cameras use photocells. I've given you like 4 now. Some television cameras use photocells. So like that. So you give 2 examples or 2 applications of a photo cell. Okay. All right. Thank you. God bless you. Don't forget to click on the subscribe button so that you can see more videos that I've uploaded on chemistry, technical drawing, math and all that, shortcut and all that. So don't forget that we have done with the part the theory part. The theory part is of two phases. The part 1 is what we have done, so we are going to do part 2, and so you click on the subscribe button for you to see the other videos I've uploaded. The objective part has been done for physics, for chemistry, and I've uploaded them and all that. So feel free to call me on 090-745-26311. click on the like and subscribe button. 090-745-26311. So we are also into home tutoring for any level, O level or A level preparation. Thank you so much. Click on subscribe button to see other videos on other subjects. Bye for now.